Hello, ladies and gentlemen, and welcome to our capstone project, Synthesis of Biofuel Additives from Ethanol. My name is Ramon Castrejon, and these are my teammates, Elizabeth Major, Nicole Van Overmeijer, and Dane Santana. Here's our design poster, and I will give everyone a quick rundown of what it contains. The introduction section includes some background and goals of our project. The design methods section explains in detail the engineering principles and techniques the team used to aid themselves to generate results. The results and conclusions section includes relevant numbers and information that comes with our design project. Finally, we included some references used in the poster, and the acknowledgement section recognizes our mentor Chris Dahl, his coworker Ben Parsley, and our design professors Adrian Abrush and Kimberly Ogden. Through this presentation, we'll further develop this information, so stay tuned. Our problem statement was to design a process to manufacture a renewable fuel additive that can be added on an existing ethanol plant to improve its profitability. The overview of this project is producing diethyl ether, or DEE, in a packed bed reactor through the catalyzed dehydration of ethanol. Moving to our design methods, the team used the POM matrix to narrow down some of the popular fuel additives. The alternative consists of 4 different synthesis paths, starting with diethylene glycol ethyl ether, or DEG, made with silver catalysts. DEG is synthesized from a tungstophosphoric catalyst reaction, ethyl acetate made from distillation, and our beloved DEE. These additives will be evaluated upon different categories, starting with economics, which includes all the costs inherent to the process and the yield of reaction. Second, performance, including fuel performance plus fuel emissions. And finally, chemical safety, which was evaluated upon NFPA ratings of the chemicals and side products inherent to each process path. As you might already know, we chose the DEE route since it was scored the highest in almost every category.
Once we had our design choice, it was now time to use Aspen to simulate our process. Optimizations were done to our process by first iterating the heat exchanger flow rates and also using Aspen's DSTW method to calculate the optimal operating conditions for the column. Once we had sized our equipment and throughput through Aspen, we were then able to cost our process using the Guthrie method, from capital investment to operation costs to depreciation to sales. Before we move on, here's a bit more info onto the benefits of DEE and why we're producing it. A blend of up to 15% DEE can reduce nitrous oxide emissions by 36%, as seen on the right-hand side, and smoke can be reduced by 6.26%. Brake thermal efficiency, or a measure of how well an engine can convert heat to mechanical energy, is increased by 15%, while the cetane number, which is a measure of combustion speed, is increased by 12%. DEE can also lower the cloud point of a fuel, making it a great additive for cold start engines.
This is a general overview of our process. It starts off with the feed coming in from the plant's beer column and ends with our distillate, diethyl ether, being sent to a tank, and the bottoms, ethanol and a bit of diethyl ether, being sent back to the plant for purification. Starting off, the ethanol is fed to a heat exchanger. This stream is then sent to an evaporator where the contents are heated to about 180 degrees Celsius, and following the evaporator, the contents are sent to an insulated packed bed reactor. This reactor is packed with silicotungstic acid spherical pellets. The output of this reactor then cycles back to our heat recovery system. This heat recovery system was implemented to reduce our energy costs by transferring the heat from the packed bed reactor to the stream that leads to the evaporator. Doing this reduces the load on the evaporator and ultimately brings down our energy costs. The table below shows our values acquired when we ran an Aspen simulation on our process. Next, the stream coming out of the heat recovery system is sent to a cooler, where our ethylene vapor is separated since it does not condense. The ethylene is then sent to the plant's dryers, and the condensed fluids are sent to a distillation column for separation. The table below shows the values that we acquired when we ran an Aspen simulation on the process, including our cooler. In our distillation column, the diethyl ether is our desired product, and it will come out in our distillate, or stream F8. Our distillate stream consists of about 93% diethyl ether by mass, with the rest being about 7% of ethanol. The bottoms, or stream F9, then get sent back to the plant for purification.
Here's a summary of the bare module cost of each piece of equipment. This was calculated using the Guthrie method, with each cost including the direct and indirect expenses of purchase and installation. As you can see, the most expensive piece is the reactor due to the cost of catalyst pellets and reactor insulation.
Continuing with the Guthrie method, the previously mentioned costs were used to calculate the total bare module cost. Then, combined with the on-site, off-site, and building costs, which are all proportional to the total bare module cost, the total permanent investment was calculated. The working capital is proportional to the sales and feedstock costs and is the sum of cash reserves, inventory, accounts receivable, and accounts payable. The working capital and total permanent investment were used to calculate the total capital investment, or startup cost, for all equipment and installation. The result is a little over $2.5 million. Diethyl ether is considered a renewable diesel and qualifies as a D4 RIN because its production emissions are over 50% less than that of diesel. As a 100% renewable fuel with a lower heating value of about 85,000 BTU per gallon, the equivalence value of our product is 1.14. Thus, 10 million gallon RINs were generated by the 8.6 million gallons of product over a year. Assuming the remaining 90% of the plant's throughput not dedicated to this process is sufficient to meet the plant's renewable volume obligations, the RINs generated by the diethyl ether are surplus that can be sold for about $12 million in sales at the current D4 RIN price. Utilities, operations, maintenance, operating overhead, property tax and insurance, and depreciation total to the cost of manufacture, which is $3.3 million. The general expenses is proportional to the previously mentioned sales of the product and amounts to $750,000. Thus, the total production cost is approximately $4 million. The gross earnings, or sales minus cost for our process, is $8 million. Deducting tax, our net earnings are $5.5 million. Given these values and the total capital investment, the return on investment is 215%, and the payback period is only 5.5 months. Assuming a minimum return on investment of 100%, the venture profit is $3 million for the first year, accounting for startup and operating costs.
Our process design was able to achieve a final purity of 93% DEE. Various optimizations, such as the inclusion of a heat recovery network, the combustion of excess ethylene, and the use of a low-cost catalyst contributed to the decreased cost of production, while DEE's higher valued RINs contribute to an increased revenue that can be generated as opposed to pure ethanol. For these reasons, it follows that our process was able to generate a 215% return on investment with a payback period of 5.5 months for the ethanol plant in which it's installed. The overall goal of our project was to devise a method to manufacture a renewable fuel additive in a cost-effective way without impacting engine performance. While DEE went above and beyond the parameters we had set, there are still several technical barriers that would need to be addressed before the widespread usage of our product. For example, while a diesel blend with 15% DEE can lower nitrous oxide and smoke emissions, it can also cause an increase in carbon monoxide and hydrocarbon emissions. Up to 15% DEE can improve engine efficiency and combustion speed, but percentages greater than that face concerns with engine lubricity. And from our analysis, it's evident that DEE can be a profitable addition to an ethanol plant. However, it might be more difficult to distribute than neat diesel due to its increased volatility. For these reasons, the results of our project are heavily dependent on the actual market reception. But in any case, the extensive body of literature supporting DEE's potential as a fuel additive leads us to be confident in our design choice. Here's our list of references. A special thank you to our mentor, Chris Dahl, and Ben Parsley from Direct Automations, as well as Dr. Kim Ogden and Dr. Adriana Bresch from the Department of Chemical and Environmental Engineering. Thank you for listening.